To begin our discussion about thermodynamics, I want to discuss the different types of phases of chemical species that you're going to encounter in this course. The first two phases that I want to discuss are liquids and solids. Now, I'm sure you're aware of the differences between liquids and solids. Liquids flow and solids do not. But in thermodynamics, we could use a lot of the same mathematical tools to characterize liquid and solid systems. Now, whenever we're dealing with liquids and solids, one of the main assumptions that we typically use is the assumption of incompressibility. And so what that means is that for a system, if we assume it's incompressible, that means that pressure is going to have little effect on the volume. Alright? So that's all the assumption of incompressibility means. And we're actually going to use it quite a bit in this course. Okay? And so, with liquids and solids, if you're dealing with, a system that's just composed of an individual chemical species, you could calculate the mass and the volume of that chemical species are going to be related to each other via density or specific volume. And so the mass and volume of individual chemical species are related by density or specific volume. And so, imagine you just have a system in which you just have water in it. If you wanted to figure out the mass of the water in that system, all you would need to know is the density, rho here, and then you would multiply it by the volume of that system. Okay? So mass is equal to density times volume. Another way you could figure out the mass of the system is by taking the volume of that system and dividing it by the specific volume. So anytime you see a V hat, that's going to be specific volume. And just based on inspecting this equation, I'm sure that you could figure out that specific volume is basically just the reciprocal of density. So that specific volume has dimensions of length cubed over mass. And so in this course, you need to be comfortable converting between density and specific volume. All right, and so if you just have a system with an individual, with just one chemical species, that's how you can calculate the mass of the system. But a lot of times in this course, we're going to deal with systems that involve mixtures of chemicals. Okay? And if you want to figure out the mass of the system in that case, you're going to have to use some sort of weighted average for the density or specific volume. All right? And so when estimating the mass of a liquid or solid mixture, you're either going to use a weighted average of density or specific volume. So either a weighted average of rho or V hat is used. Okay? Alright. And so there's two different ways to approach this. You could either calculate an average density, and so the little bar on top here is what I'm going to use to symbolize averages. Alright? And so your average density is going to be equal to the sum of the mole fraction of a chemical species times its individual density. All right? And so if we calculate an average density in this way, This is known as the principle of density additivity. Alright? And so if we use this average to calculate the mass of our system, we're assuming that the system follows a density additivity principle. In a similar manner, you could also calculate your average specific volume, right? Which is also just, a weighted sum of these specific volumes multiplied by their individual mole fractions. Okay? Another way to write this, based on the relationship we had earlier, is it's going to be a sum of your individual mole fractions divided by their individual densities. Okay? And if you use this average to calculate the mass of the system, what you're assuming is that the system obeys volume additivity. And the reason I kind of make a big point about this is because typically a weighted average based on density additivity is not going to be equal to your weighted average, or the reciprocal of the weighted average via volume additivity. Okay, so those numbers usually are not equal to one another. So depending on what you use, either rho average or v hat average, you may get a different number for mass. Okay? Now, both of these assumptions here, I just want to point out that both of the assumptions here assume that there's no interactions between any of the components in the mixture. So both estimations assume no interactions, no molecular interactions between mixture components. All right. Now, whether you should assume density additivity or volume additivity, the answer to that is it depends on, the system that you're working with, because each estimation, works better for some systems than others. Systems than others. All right. And in the end, if you want a true measure of, what the average density of the system or the average specific volume of the system, and really if you want a true measure of the mass of the system, experimental data is always going to be the best. Nevertheless, these sort of approximations are useful when we're trying to characterize, the mass or the volume of our system.